Hi, this is notes about the ideal gas law. So the ideal gas law is going to be having the variables of pressure, volume, temperature, and moles, which the combined gas law did also, but the combined gas law, if you remember, it always has like that. Let me just write it now. So this was the combined gas law. So it would be like a beginning pressure, and then the pressure changed to a beginning volume, and the volume changed to. So it was always two different sets of conditions, whereas the ideal gas law is just one set of conditions at any given temperature, pressure, volume, number of moles. So the equation is PV equals nRT. So P is pressure, and we're going to, I'll show you, but for the most part, we're going to want to have our pressures in atmospheres. I'll explain that more coming up. And the V is for volume, and our volume has to be in liters. N is for mole. T is for temperature, and that has to be in Kelvin. And then R is the gas law constant. And the value is 0.0821. And then the unit is liters, atmospheres. Those are multiplied over Kelvin mole. And I'll show you how that gas law constant has to be put into the equation in order to be able to use it, but it also can show, and I can show you how the units look kind of scary, but they actually help if you keep them in there, and then you can see everything cancel. So there's different values for R. The one I just gave you is right here. So this is when your pressures in atmospheres, volumes in liters, temperatures in Kelvin, and moles are moles. So you can see in this graph, which is in your book on page 384, not graph, table, the volumes, and we'll just ignore this one. I never use this one. But the volumes are always liters, temperatures Kelvin, but you could use a pressure in millimeters of mercury, and then you would have to use this value of R, or kilopascals, and then you use this one. I think for the most part in my answers, I always use this one. So if I were given a pressure in a different unit, I would just convert it to atmospheres. But you can do it your way too, if you want, and choose to not convert your pressure, but then choose a different R value. Your answers might be a little different than me just because of rounding, but don't worry. So let's do some of the examples together. So I think I have 4 of them, and they're all a little bit different. So this first one, let's just kind of read it and list what we're given and what we're looking for. So they want us to find the moles, so that would be my unknown. And it's 20 liters, so that's my volume of gas. And it's in the correct unit, so I'm good. The pressure is 200 atmospheres. And then the temperature is 27, which I'm going to convert that into Kelvin. So I would add 273 on. And, sorry, let me just do that with you. I have to find my, okay. So I would add 273, and then I would get 300.0 Kelvin. And then my R, because my pressure's in ATMs, I'm going to use 0.0821 liters atmospheres over Kelvin mole. So now this is just getting me set up for the problem. I'm going to just put a little squiggly, and then we're going to do the problem over here. So PV nRT. You can solve for n first and then put the variables in, or I'll do it, I think the way more common that you do it is to put the values in and then rearrange. So I'm going to do, so this is my P. This is my V. So PV equals N is my X, R, I'm going to hold the unit out this for time and space. I'll put the unit in now when I start to manipulate it. And then temperature. So the algebra, we would divide both sides to get that N alone. So when you do the math on your calculator, you're going to need to, I'm going to put that unit back in to show you how cool it is. You will have to use parentheses in the denominator, or however works for you with order of operations. So N equals, I would multiply 200 times 20 divided by parenthesis 0.0821 times 300. And I just want to show you with the unit, you can see that my kelvins cancel, my ATMs cancel, my liters cancel, and I'm left with 1 over mole, which ends up flipping and becoming just mole. So my answer here is, this way I don't have it calculated, hold on. So my answer is 162 moles. So when you do the sig figs, you can kind of look at your beginning numbers, and I will give you some leeway here. So I'll probably grade you plus or minus a sig fig. So this has 3, 4, and 3, so I went with 3. All right, let's do another type of problem. So here we have, I don't know why I'm always in the way. Let me move me. In this question, we're being asked the volume, and we have 150 grams of oxygen, and we're at STP. So if you remember from previous presentations, that means the temperature is 0 Celsius, which is the same as 273 Kelvin, and then the pressure is 1 atm. I'm going to use my R, and the problem that I have here is I do not have moles, but I have grams. So I can take my grams of oxygen and convert that using my molar mass into moles. So when I do that, I get, 4.69 moles of O2. So then I'm ready to plug into the equation. So P V is my X equals N R and then T. So I would divide both sides by 1 atm to get the volume alone. And when I do this, I get, with 3 sig figs, I get 105 liters. And again, I can just show you the units. You don't have to do this, but I like to, because it really shows that you did it correctly. All right, I've got 2 more examples. So this one is the normal human lungs can hold about 6 times 10 to the 3rd milliliters of gas, and we're being asked for the number of molecules. Our pressure is 1.01 atm. Our temp is 21 Celsius. So I'm going to convert that to Kelvin. And then I'm going to use my R. So my unknown here is going to be moles, and then I can use Avogadro's number to calculate molecules. So I'm going to let you guys pause the video and then try it, and then restart the video and see how you did. So you can check your work with mine. Just one thing, hopefully you caught that you would have to convert your volume. Always has to be in liters, so the milliliters had to be converted into liters. So I'm going to use 6 liters. And then when I plugged in up here, I got 0.25 mole. And then the question's asking me for the number of molecules, and we know that 1 mole of any kind of gas has 6.022 10 to the 23rd molecules. So then we can just multiply 0.25 times Avogadro, and we get 1.5 times 10 to the 23rd. One last question. So this one's a little different again, because I wanted to give you lots of different types of problems. This one's 0.88 grams of an unknown gas are collected in a 562 milliliter container at 25 Celsius and 744.8 millimeters of mercury. And we're wanting to know the molar mass of the gas. So molar mass, remember, is grams per mole. So we have the grams, and we're not going to use that until later in the problem, after we use the PV equals nRT. So what we're going to need to do is solve for N so that we can get the moles and use the grams. Then we'll get a molar mass. Then we'll look at the periodic table and see which element we think it is. So just little hints here, and then I'm going to let you guys pause the video and try the problem. You do have to make sure your volume and pressure are in the correct units for you to use the ideal gas law constant. So I would pause your video, try it, and then unpause. Okay, so this problem had a lot of little details to it, didn't it? So the volume had to be converted into liters, the temperature into Kelvin, the pressure, I went to ATMs. You could have left it in millimeters and then used the other value of R, which I think is 62.4. And then I used my regular R, so that's why I went to ATM. Then you want to plug into the equation, and our X is N. So when I solve for N, I got 0.0225 moles. And then molar mass, because we know molar mass is the number of grams of that substance in 1 mole of that substance, then I'm going to now use this mass that was given and divide by my moles that I just calculated right here, and I get 39 grams per mole. And then I look on the periodic table, and the element that is closest to that is argon. That's all I have. Hope that helps.